attending the course and taking it much more seriously. But now that we are getting to something that's really interesting and they are useful in the application, people are missing. And it's okay. Let's start. Today we are going to talk about some mathematical tools, mostly seen in the machine learning stuff. Machine learning, in general, it's a very, huge topic. So it contains so many subtopics, including the signal processing. But there are some mathematical things related to the machine learning theory, which are really useful in signal processing. We have to mention those things, and in the applications that you will see in the speech processing, image processing, and computer vision, you will frequently deal with this kind of mathematical basics. So that's why we dedicated this lecture for this three of those important topics that we have to mention. So singular value decomposition, principal component analysis, or PCA, which has the other names, KLT. There are some articles you see that it's written KLT, or Karhunen-Liouville transform. That's the similar thing, similar name for the same idea. So the PCA and KLT are the same, or sometimes you see somewhere Hotelling transform. These are all three names are the same. So, and finally the linear discriminant analysis, or LDA, and PCA and LDA are frequently used in recognition stuff. Most of the applications that deal with the recognition, you see that PCA or LDA, they are used in one way or another. So let's start with some basic linear algebra things. So when we talk about the linear, first of all, in the beginning lectures, we actually talked about the linearity, and we mentioned that linearity gives us a lot of advantage. And among those advantages was the superposition property of the linear, any linear operation. And in linear algebra, we have a very rich theoretical background in the case of linearity. That's why it's called linear algebra. And this rich theory actually helps us a lot in many domains, in areas of signal processing, machine learning, and many other things, many other areas that have overlapping with these general topics. Assume that we have a linear system of equations, which can be denoted as y equals to ax. So x is the input, or the domain for this equation, and a is the matrix, which actually tries to transfer everything from the domain x to the range y. So every data in the domain, which are represented by x, they are transformed to another domain, or the same domain or another domain using y, using a, and gives y. Now the point is that any linear transform could be interpreted as one of the three tasks that is mentioned actually here. One of these tasks is actually is applied when you are doing this linear transform using this A matrix. Either this A matrix is doing the rotation, or it's doing the dilation, which means stretching or compressing. So any vector that we have in the domain, and can be mentioned like x using the Cartesian coordinates, or the polar coordinates using x and y, or for example in 2 dimensions, or r and theta, no difference. But applying this A matrix in a linear system of equations, it actually gives us a rotation to that vector. Like here is an example. You see that if this is the vector, then by doing this kind of, this is the linear A matrix that we are applying actually, and it contains the elements which are the cosine of this theta, which theta is actually here assumed to be 45 degrees. So if you apply such kind of A matrix to the vector 1, 0, one of the unit vectors of this domain, this coordinate, Cartesian coordinate, you will get to this point here. So you will see that it's a kind of rotation that we are actually applying to this vector. And if you apply such kind of matrix in this to the domain, if you apply such kind of matrix which is diagonal with the same values on the diagonal vector, then you're actually, based on this alpha, whether it's alpha is greater than 1 or less than 1, you're actually stretching or somehow compressing this vector. Or it can be, this A can be a combination of these. So it could be rotation and dilation, or a combination of rotation and dilation together. So using this basic, now we have another concept we have to talk about, and then we can go directly to the ideas of SVD and PCA and KLD and LDA. So let's talk about the singular value decomposition. Going back to the dictionaries, assuming that every vector in every domain, it could be spanned by the kernels or the basic elements of that domain. So if, for example, x of n is a data point which can be represented completely without any losses in a domain, we can have an example of that in the, for example, if you consider this x of n to be a data point about the position of any source in the three-dimensional space. For example, some point inside this room as a three-dimensional space, then you can easily represent any point in this space in the Cartesian domain using the unit vectors of the Cartesian domain, which are, for example, I, j, and k, alongside the axis x, y, and z. So that's exactly the same thing. So if xn is a data point which actually can be interpreted as a position in the room, then it could be generated or synthesized based on the kernels or the basic vectors of that domain, of that space, if they are completely spanning the data points in that domain. So what actually, it can be shown that what actually you're doing is, for example, if this is the space, three-dimensional space, x, y, z, and you have the unit vectors I, j, and k alongside this axis, x, y, and z, every point in this space, if it's a room, for example, if it's a three-dimensional room, then every point, and for example, if you consider this one to be the origin, every point in this room with respect to the origin can be considered as a vector, and assuming that this is x of n as a data, then it can be represented based on the basis vectors of this environment, of this room, of this domain. And these are the basis vectors, I, j, and k. Or they are the dictionaries. They are the atoms of the dictionary, or they are kernels. Now, if you want to represent x of n based on I, j, and k, what you actually do is that you are if this is, for example, the vector corresponding to x of n data here in the environment, and this data in general is actually representing the position of the source in the environment, then you do the projection over any of these axes. By doing the projection, assuming that you do the projection onto y, x, and z, what you get is actually x of n, which can be represented as alpha times a plus beta times j plus gamma times k. So you see that the vector in that domain can be spanned based on the basis vectors with some scaling. And that scaling, alpha, beta, or gamma, they are nothing but the amount of projection. So alpha is nothing but the projection of x of n onto the basis vector I, and the beta is the projection of xn with j, and gamma is the projection of xn and k. I, j, and k are the basis vectors. In the same fashion, if x of n is a data in any domain, and if ui's are the vectors or the basis vectors which can completely represent that domain, represent any kind of data in that domain, or data in that domain can be spanned based on these ui basis vectors, then you can synthesize x of n, or in other way analyze x of n based on these kernels by writing it like this. So you have, for example, d dimensions. Because you have d dimensions, you should have d basis vectors to represent that data at least. And you have the ui's as the basis vectors times how much, or the scaling of that basis vector. And this scaling is nothing but projection. Projection of data onto ui's. And projection can be represented in different systems of mathematical systems. So if you have, for example, the vector case, you can just show it by the inner product. In the linear algebra, you can just show it by inner product. That's the projection. Or you can use it as, for example, the vector form. If you can write it down, xn transpose I is again the projection. This is also inner product. If you have random signals, then what happens? The same way. So transpose the other. You have x as a random signal, the other one j, for example, or y. Then x transpose j. It shows actually how similar they are with respect to each other. What we said about the correlation. So correlation is also a way to represent how similar they are. So this is how we can actually explain x of n based on the basis vectors in the domain that xn is actually spanned completely. We actually saw the same thing in the Fourier domain. So when we talked about the Fourier domain, we said that these e to the power of j omega n, they were actually, we called them as the eigenfunctions. And those eigenfunctions are nothing but the kernels or the basis vectors that every signal, which is actually defined in the Hilbert space, can be represented based on those eigenfunctions. So those eigenfunctions in the Fourier domain, they were actually the kernels or the basis vectors in the Fourier representation. And they are actually in DFT domain also, they have this correspondence. So e to the power of j 2 pi over n and k, which is is actually a kernel or a basis which contains two parameters, n and k, one representing the time, the other one representing the frequency. And every signal in the DFT domain can be represented based on this kernel. So whatever comes as the coefficient is just the scale or the projection of that signal onto this vector or the basis. These are the sample or another view of all the things that we actually talked about in representations like the Fourier and Z domain or whatever. So those transforms, they are actually transforming to another domain, which those domains are actually containing their own basis. Now the point is that SVD is a kind of transform which enables us to use this actually representation based on the statistics of data and adaptively. So you are not taking a constant basis like the one that we had in the Fourier. In the Fourier domain, you have constant basis, and every signal is just projected onto these bases, and you take the amount of those bases as the coefficient. But in the SVD, what we actually do is that these bases are adaptively changed based on the statistics of the data. So these bases or the kernels, they are adaptively taken based on the statistics of data. So one of the merits of SVD with respect to other transforms is that SVD actually can represent the real dynamic of the data. What it actually means is that assuming that, for example, you have, there was a nice example from one of the professors in Washington University, Seattle, Professor Kutz. He said that assuming we don't know anything about the gravity, and for example, we're coming from another planet. We have no idea about the gravity. There were no Newton there to talk about the gravity. But they have already progressed, and they have cameras. If, for example, we use a system of spring and mass, like this, there's a mass and there is a spring here. And if you, for example, push the mass with some force F through a direction, doesn't matter, for example, in this direction. But you take the cameras, for example, 6 cameras, and you put them in different places. For example, one camera here, one camera here, one camera here, and so on. So because you are actually gathering the data with 6 cameras, it's pretended that the dimension of the data that you finally get is in 6 dimensions. So you're actually getting the information of this dynamic, because when you push this mass to one direction, what happens is that it starts actually oscillating. This oscillation or dynamic of this data is actually captured by these different cameras that we have. Now the point is that it seems that we have x1 to x6, for example, 6 different dimensions for the dynamic of the data. Looks like that. But the point is that if you apply SVD on this data, on the data you're captured, for example, for 1 second, in every row it's actually the time data for 1 second, and you have 6 dimensions. Then it contains a matrix, and then you apply the SVD on that matrix. If you do that and then try to extract out the parameters of the SVD, for example, the eigenvalues and eigenvectors, then you see that it actually gives you one of the eigenvectors having actually a large amount of eigenvalue corresponding to that, and for the rest of the eigenvectors that can be extracted, you see that the eigenvalues which are assigned to them is actually close to 0. It actually implies that there is only one vector which is capturing the most scattering of the data around. So the data is oscillating around one of these vectors and not around all of them. And it's implicitly telling you that there is just one way, because if you stop, pressing anymore, it's just mentioning that, implicitly mentioning that there is just one direction that captures the most dynamic of the data. And when you go through that, you see that this direction is the direction of gravity. Yes?
So is the PCA a special case of the SVD, because that's the same?
PCA is actually is the result of SVD.
Okay.
So if you just take out the most important eigenvector and throw away the least important ones based on some measure, then you are doing PCA. So SVD actually gives you the entire dynamic of the system. It gives you the eigenvectors and eigenvalues. Or another way, based on the statistics of your data, SVD gives you the entire information about the dictionary which the signal is actually constructed on those basis. That's what SVD does. In general, SVD is actually a factorization or decomposition. It takes a matrix A and tries to decompose this matrix into 3 different matrices. So in linear algebra, you know that every kind of transform, for example, if we apply this A to the x vector, first of all, this V is applied, V conjugate is applied. Then the second thing that's applied is this operation. Then the third one would be the U operation. So from right to the left is the order of which these matrices are applied to the data. So A, the matrix as transformed, the linear transform matrix, is decomposed into 3 different matrices. U, V, and sigma, and this beginning and the end, they are unitary transforms, so they do rotation, and the one in the middle, it just does the dilation, so compressing or stretching. That's why this sigma is diagonal, and U and V, they are unitary transforms, which actually they perform rotation. And you know that the unitary transform has some properties in the linear algebra. One of them is that the inverse and the conjugate are the same. So inverse of these matrices and the conjugate of these matrices, they are the same. And this factorization is what actually SVD does. How to get to these U, sigma, and V values actually for these matrices? We can actually get from this slide, and then we'll be back to the comparison between SVD and EVD. So in order to get this decomposition, which you can have a MATLAB command for that dedicated for SVD, and you don't need actually to go through the details of how to get these matrices. You can just easily write down SVD of any matrix, and it will give you those 3 matrices, U, S, and V. But in general, in order to get it, you have this A, so you make an A transpose and multiply that by A from right and left. When you apply that from the left-hand side, then you say that, okay, this, when applied, should give me actually, because we know we want to have this kind of decomposition, that A is u sigma v conjugate. So you transpose this A and apply it from left and right, and then you will have the V and the U as the eigenvectors and the sigmas as the eigenvalues corresponding to them. The same as how you can extract out the eigenvalues and eigenvectors for every kind of matrix. When you apply that for these two cases, you can extract out the values for the eigenvalues, and the relation between the sigma and the lambda, the capital lambda, is that they are actually the variances, and these are like the standard deviations. So that's the square root of them. That's all. And this V and U are the eigenvalues and eigenvectors for the A transpose A matrix or the AA transpose matrix. You get these values and make this decomposition. When that happens, yes.
So V is the eigenvectors of A transpose A, right?
Yes.
And how is it, row or column? I mean, like the eigenvectors are arranged in columns or rows?
Eigenvectors are always column-wise.
So
Yeah. It's by default everything is column-wise.
Lambda is the variance.
Lambda here. Lambdas are actually the variances, and these sigmas are actually the standard deviations. So they are the square root of these variances. And these square roots are called singular values. So the square roots are singular values. And it's clear because we are actually doing the A transpose A or AA transpose. So we are actually getting the energy of matrix. So it gives us the energy of those eigenvalues. So in order to get the one that is actually corresponding to the A itself, we need to get a square root. Here you have a quadratic form, and what we actually need is a root of that, a square root of that. So that's why we actually, when we have something like this, we actually apply this square root. And it's so simple. So A transpose A, if you assume that there is a kind of if you assume that there is a kind of decomposition for A like this, then A transpose would be V conjugate transpose, sigma transpose, U transpose. Then you apply AA transpose, what should be the result? If you apply AA transpose, the point is that it becomes U sigma V conjugate times like this. Then V is unitary. So what is this? This is just an eigenfunction. This one, again, is nothing but sigma square, and you have U sigma squared like this. Okay? So AA transpose is U sigma square U transpose. Okay? Now you know that U is unitary. Because it's unitary, U transpose is U inverse. Apply that from the right hand side of both. So you apply U from right hand side, you get AA transpose U equal to U sigma square and U inverse U, which becomes the eigen matrix. And what you get is this. Okay? Now if you apply it conversely, you will get the other one. Okay? And it means that if you want to get, so if you look at the form of the equations, it's so clear. we always had such a thing that, for example, for a kind of matrix which is called X, if this is the X matrix and you wanted to extract out the eigenvalues and eigenvectors, you would definitely write it like this. For example, you said if Vx equals to lambda x, then these V vectors were eigenvectors and lambdas were eigenvalues corresponding to the vectors. And you see here, instead of V, we have A transpose V or U. And instead of this one, you have U sigma square. Well, here if you had just a single value, but if you have a matrix, then you have to actually turn it around and flip the location of these two. And you will get this. So that's playing the role of V, and this one is playing the role of num. But you know that we were actually looking for A, the vectors, eigenvectors and eigenvalues of A, but now we have a quadratic form of that. It's like square form of that. Because it's a square form, you get the values, the square of the values or the eigenvalues. So you have to make a square root of that in order to get the singular values. The same for V. Okay? So you get the values for the U and V and the singular values. And you sort them in this way, you will get the decomposition for A matrix. So one of the advantages is that if you make this kind of decomposition for any matrix A, then it would be so simple if you need something like A to the power of some M. M should be anything. Because it's just like to apply that exponential term, to apply that power on the eigenvalues of the diagonal matrix. That's all. You can test it for M equals to 2, 3, and then you will see that that's the only thing that happens. Whatever this power is, it's just applied to the values of singular values, actually get to that power. So it's very interesting. But there is another concept that in many articles you see, eigenvalue decomposition. I just mentioned this slide to say that eigenvalue decomposition is pretty much the same as singular value decomposition with a very slight difference. And that difference is actually showing here. In EVD or eigenvalue decomposition, if you are asked to get the decomposition based on EVD instead of SVD, you're actually getting the same thing, V, sigma V conjugate or transpose. That's EVD. But what it actually happens is that EVD gives us the transform in the same domain. SVD actually gives us the transform to another domain. So you have the V in the initial domain, the primary domain, and in the range you have U. So one rotation would be happening, the V rotation, which is the first task with the first operation from right hand side is the V operation. V is actually applied to the X. V is applied in the same domain that the data X is actually located. And V was supposed to be a rotation, a unitary matrix, which actually represents a rotation. After doing the rotation, then sigma is applied, which is a dilation, stretching or compressing in the same domain. Then is transferred to the another domain in the SVD using another rotation, which is called U. But in EVD, you're doing all these rotations in the same domain as the data is. And because of that, EVD sometimes fails to actually give you the decomposition, but SVD always applies. If matrix A has some singularity points, then EVD probably fails to give you the decomposition. If A is rank deficient, if matrix A is rank deficient, and rank deficiency means you can definitely find one of the rows or columns to be as a multiplied version of the other row or column, then, or the superposition of that, then this matrix is rank deficient. It means that there are rows or columns that have some redundancy in the information. Actually, they don't give you any more information, and there's some information missing. If the real dimension of the data is, for example, n, but you have a rank deficiency, it means that part of the data cannot be represented in that by that matrix A. So if the matrix A is rank deficient, then EVD fails. But SVD doesn't care about the rank deficiency of the matrix A and always give you the answer. And that's the good point of that. So SVD always works. That decomposition, SVD, always works. Even if A has the rank 1, the minimum rank, it always works. You can find a decomposition like that. So, some other notions that we have to take care, and they're important, are the notion of norm. So we have different norms, and norms are measures of the distance or the measure of the size of the vector in different spaces. So we have the 2 norm, and for the 2 norm is actually giving you the first, for a matrix A, it actually gives you the sigma 1 or the singular value, the first singular value. You know probably the notion of the values, eigenvalues and eigenvectors, or I can mention again. So what is eigenvalue and eigenvector? Assuming that there is a data scattered in the 2-dimensional domain, and this is x1 and x2. So you have data scattered in some way. And this is your data. Then the eigenvalues, if you're looking for eigenvalues and eigenvectors, what are you actually looking for? The notion of eigenvalue and eigenvector is that the first eigenvector is the vector or the direction which the data has the most scattering alongside that vector. And you probably confirm that this vector, this unitary vector, is actually the first eigenvector, because most of the data has been scattered alongside this vector direction. And the amount of which data has been scattered around it, or the variance of data around this vector, alongside this vector, is called eigenvalue. So if I say about the eigenvalue, this is the eigenvalue, and this is the eigenvector. The first eigenvalue and the first eigenvector. Then the second one probably would be vector v2, and this would be lambda 2. And because we have the data represented in a 2-dimensional domain, we are not actually looking for something more than 2 vectors and 2 eigenvalues. Okay? So this is actually the notion of eigenvalue and eigenvector. And when we say we're looking for eigenvalues and eigenvectors, we are actually looking for the directions and the variances of the data being scattered alongside that directions. That's all. So the 2 norm of any matrix is actually the first scattering, the first deviation, the first actually standard deviation of the data alongside the first vector.
I'm sorry.
Yes, please.
As the first vector means that in this direction the data changes most.
Data changes mostly in this direction. You see that the data is scattered mostly in this direction.
And the second.
Or the variance of data, the variance varies alongside this vector more than any other side. So that's the direction of the most variance or most scattering of the data.
And the second.
And this one is the second, which has the most scattering.
But it is also similar to the first vector. I mean,
It's also orthogonal to the first one.
yeah.
Yeah, this is the orthogonal to the first one. So, the Frobenius norm of a matrix, the squared of the Frobenius norm, is actually the sum of the squared of all those singular values. The second option that we have here. And the ratio,
What is the use of the Frobenius norm?
you'll see here. So, and the ratio between these two is actually giving you a value, and this value is, if it's this value, for example, more than 95%, then it means that less than 5% of the information is actually scattered around the other vectors. So it means that if, for example, you can have this kind of measure and you put a threshold on this value, this ratio, and for example, if this ratio is 98%, you can ignore those 2% as a noise.
So you just need the one vector and you can ignore all the other vectors. So
Exactly.
thanks.
You can ignore the others. Another way, if this value is more than 95%, for example, it says that this data has a dynamic only alongside the first eigenvector. And whatever eigenvector is, you can get it from the decomposition.
And if, let's say, it's a really low value, that means that data is distributed arbitrarily in so many directions, right?
Yeah, it means that the real dimension of the data is too high. It has values in all the dimensions.
Okay, and how good is that? I mean, like that.
Practically, it rarely happens. Most of the dimensions of the data are actually useless. Most cases it's useless. You always have some redundancy in the data, and that's why the compression is something that comes to the mind of the engineers and scientists. And they do the compression. And there is no practical signal I saw, at least so far, that you cannot do any compression on that. Every data has some redundancies, like images, like speech, they have redundancies.
So this means 0.95 and not 0.95%.
Yeah, exactly. The percent is wrong, actually. You have to. Yeah. Yes?
So is this just from the first eigenvector?
It means that the first eigenvector, yes, that's the first eigenvector.
So could we just do it for all possible eigenvectors and then choose?
You don't need it, actually.
No, the first one is the only
You
one.
don't need it because the first one is the one that actually the most of scattering of the data is around. So it's always the most. I don't care about the direction, what is it? I don't care about that, but whatever it is, it contains the most variance. You don't need to go through the others.
Could we take them to improve our result?
Of course.
Just take the second
That's what
result?
PCA does.
Okay.
So you got the idea of PCA, and PCA is actually doing that. So the determinant of the data is actually just as a notion, you have to know that. So when we talk about the determinant of any matrix, what we are actually talking about, what is determinant? Determinant is actually, of any matrix A, is actually representing a kind of property that comes from that diagonal matrix. And what is it? It's actually the product of all singular values. That's the determinant. If you have a vector, what is the determinant? What is the notion of determinant for a vector if it's not a matrix? Size of the vector. That's the size of the vector. And when you talk about the determinant in this, for example, two-dimensional case, you're actually talking about lambda 1 times lambda 2, square root of lambda 1 times lambda 2. Okay? So determinant actually shows, you know, the surface or the area which the data is scattered onto that area. Is a notion of size on the surface, depending on the dimension. Now, let's go for the application. So we saw that every matrix A can be decomposed like this, as U sigma V conjugate or transpose. Frequently I change the transpose conjugate because in this case they make no difference. They are unitary transforms, and you can use conjugate, and you know that conjugate and inverse and transpose, they are the same. So otherwise, I would not replace these different things. So simply because you know that this sigma values here, they are actually representing the singular values. What you actually can do is just, instead of this, you can write it down based on expansion. So if you do the expansion, you will get this expansion. So A can also be represented based on these unit vectors, Ui and Vi, if you assign this Uj or Vj or Ui and Vi. Then you can have this kind of expansion form of the same thing. So this is in the matrix form. This one is in the expansion form. It can be represented like this. And the point is that we can investigate whether we can limit, actually the upper limit of this, we can decrease it from R to N to be something much less than R. If we can do that, then we have an approximation of that matrix. Is that okay? So we can have the approximation of that matrix. If we apply N instead of R, in other words, we just take N vectors out of the complete R vectors, U and V. And what does it mean? It means that the difference between the real A and the approximated version of the A, the difference will actually be the singular value n plus 2, n plus 1, which is actually the residual. And it depends, if this approximation is good, then it means that this should be very small. Exactly. So if this value is very small, then this approximation is very good. And about the Frobenius norm is actually the square root of the sum of a square of all the other residual singular values from n plus 1 to the end. Now, the idea of PCA comes in. Motivating the PCA, then we will go through how to get these PCA values just based on this SVD. Later you will see that there are different other ways to get the PCA transform, but SVD, as I started the lecture with, is the most, the easiest way to actually go through the SVD to PCA is just using the SVD. So now the pre-simple component analysis, which as I mentioned are coherent of transform or Hotelling transform, the other names for that, tries to actually get a high dimensional data and tries to actually project it in such a way that the data as a result is having actually much less dimensions. But this projection is done specifically So we are actually projecting the data on linear hyperplanes actually. So as it's defined here, what we are trying to do as the goal of PCA is to find the number of orthogonal dimensions like V1 and V2 here. We are trying to project the data onto these orthogonal dimensions in such a way that it has the maximum variance over these dimensions. These dimensions, which are actually the eigenvectors. And this should be orthogonal. So the condition is that these are orthogonal. And when you project the data onto these dimensions, you're actually getting the maximum variance over these dimensions. By doing that, then if we see some of these dimensions, they have the minimum variance, which are less important than the others, based on the approximation idea that we actually mentioned in the norm case, then we can probably say that some of these less important dimensions belong to the noise and we can ignore them. By doing that, actually we are sparsifying the signal, or somehow you are getting rid of the noise from the signal. You're getting the most important part of the signal, which is located actually for the maybe the n dimension, and then you will ignore the rest of the n dimensions. So it's actually the orthogonal projection onto a linear hyperplane. So hyperplane, when I say hyperplane, in the one dimension hyperplane is nothing but line. And for this two-dimensional space, the hyperplane is just a plane. And for multidimensional space, it's just called hyperplane. It's a linear.
No,
Yes.
For 2 dimensions, it's a line, right? Because for 3 dimensions, it's a plane. For 2 dimensions, it's a line, right?
For 2 dimensions, it's line. Yes. Yeah. Yeah. For a two-dimensional space, it's a line, and for more than that, it's just that -1. So it's plane, line, plane, and hyperplanes. So you are actually doing this kind of projection. And there is a very slight difference, or it's not a slight, it's actually a big difference, but very similar things that might happen. Some of the students, they say that, okay, what's the difference between the linear regression and the PCA? It's, you know, if you just look at the way that they performed, so the linear regression is actually you're having a line, and then you're actually vertically making these distances minimum as possible with that line. But in PCA, you're actually projecting everything onto that line. Okay?
Oh, okay. So the difference
So you do the projection onto that line. But in regression, you're not doing the projection onto that line. You're just doing everything in a vertical format.
So the points remain as it is in linear regression, but in PCA we project those data points on this.
Onto the line, and then we talk about the idea. So that's the entire thing about the PCA algorithm. First of all, we have to do some pre-processing. We centralize the data around the mean, and then we normalize the features. And we do that for many projects, because there are not, you know, we have some kind of data with different dimensions that they are not actually looking the same. So one dimension, it might be, for example, in the scale of 1 million, and the other dimension would be in the scale of 0.1, 0.2, something between 0 and 1. So you see that kind of representation would be, you know, so wildly represented, and it's not possible to have a good intuition out of that. So it's better to normalize everything for the algorithm. The scaling of the computation would be almost the same if you normalize that. If you normalize by the dynamic range, actually, what you are trying to do is actually you're doing all the processes in the same domain, in the same scale. So we have the centralization of the data, and centralization is nothing but subtracting the mean out of the data. And we do the normalization by using the standard deviation of any of those dimensions. And by that, you have the data actually, every data sample for any dimension, scaled and normalized and centralized. Then this is the new data. Still nothing has happened. It's just changing the scale and the centralization. But then what you do is you actually make the covariance matrix created, sample covariance matrix. Well, here it should be n, or this one should be m, which is the same. So you make a sample covariance matrix. When you do the sample covariance matrix, and sample covariance, as I told you, is just a projection. You're actually covariance is a resemblance measure. How much two things are similar. So you compute the covariance matrix, and then you apply the SVD on the covariance matrix. When you apply it, you will get these unitary matrices and this S, which is actually the diagonal matrix, and shows the dilation, compression, or stretching. Then the point is that k columns of this U, as you mentioned actually, there are k columns of this U which might get the most energy of the signal, and the rest are just belonging to the noise. If you, for example, get the first and the two norm, the ratio between two norm and the Frobenius norm, and then this amount is, for example, around 80%, then it's not good enough to just take one direction as the most important direction. So 80% is not good enough. But what if we take k first dimensions and then we come to 98%? Then 98% is a very good approximation. And this k in many real applications would be much less than the real dimension of the data. For example, you have data in 1,000 dimensions, but you see that only 20 dimensions are important. So that's the scale in the real application. So we have to choose k columns of that unitary matrix U that can approximate the data very well, based on the measure that I mentioned in the previous slides. And then you just apply this U matrix to the data. What you get is approximation. And because U is already reduced, so the Z as a result is actually the compressed version of the data X. And it contains most of the information of the data, the original data. But the dimension of X would be, for example, 1 million, and the dimension of Z is around 40, 50, something like that. And you see that the computation is simplified a lot when you have the compressed version of the data using the PCA. So, how to choose this k? One method to do that. So we saw that approximation of X would be U times Z, or the other, just look at this one and then apply U transpose from the other side. We'll see that. Now the point is that how to choose this k. So the approximation is, we have the data and we make the approximation of the data and take this ratio, which is actually the Frobenius norm here, and this approximation, the two norm of the approximation. If it's less than 1%, then it means that all the data can be captured in that approximation. So you change k until you reach 1%. So you start doing PCA with k equal to something. For example, k equal to 1. Then you go to 2, 3, 4, until you get to the 1%. When you get to the threshold of 1%, that k is enough for the approximation. Okay? So you got what we have to do. We have this matrix A, decompose it, then you take this, you take the reduced version of that using k equal to 1, and you reduce times x times z is actually the x of approximated x. So you already have z as the approximation. Now the point is that the difference between real one and the approximated version of x the true norm of this over the Frobenius norm of the x itself, this should be less than 1%. So you start with k equal to 1 and then repeatedly go to something, for example capital K, unless this happens. When this happens, that k is sufficient to have all the information of that data. So there are other ways to actually represent the PCA or to get the actual projection, the PCA actually projection as a function. And they are just by using the idea of the PCA, the original idea of the PCA. So instead of using SVD, we could have, for example, the one view to say that, okay, by projection, what we mean actually, we need to do a projection W transpose onto X in such a way that these conditions should happen. So the projection should give me the maximum variance. So the maximum variance for this projection, so this is whatever you get as the output matrix or the data. That's the output. You want to have the maximum variance here. The maximum variance is just true norm squared. That's the maximum variance. So true norm of this projection, so the projection is W transpose X. Variance to be maximized means that true norm should be squared. So that's the true norm squared. And you're looking for a kind of W which gives you the maximum of this. So R max is actually searched. What you're searching is arg max, the argument W, such a way that applying that W on X as a projection will give you the maximum variance. But you have limit, we have to apply a limit on W, because if you just leave it like that, then the W can go widely, can be too high, but you limit the norm of W to be 1. So the norm of W, true norm of W to be 1. That's the limit that we put here. So the norm, or the size of the norm squared to be 1, or the variance of the W should be 1. Doesn't make too much difference. And this is the condition. So you have actually a kind of constraint optimization problem, which you are looking for a W. So W of PCA, W of PCA that you're looking for is the argument of this function, a W, which maximizes this cost function. Actually, the objective function, not the cost function. Maximizing this objective function. And this objective function is the variance with this constraint. And when such kind of constraint problem you have, you can easily, because this is convex, quadratic form is convex, you can easily use the Lagrange multiplier. It means that you can assign objective function to be the real objective plus a regularization term times the constraint so that's the new objective function, and you ignore this, and then easily you can just take the gradient of this with respect to the w, equalize by 0, and get the w values. And if you get it and do these calculations, then you will get to this point. You will get to this point and you can get the w values that fulfills this equation, system of equation. The second view is actually the idea of we want a kind of projection in such a way that, so finding the subspace in such a way that we get the least square of the error of projection onto that space. So W transpose X is a projection, and what you're trying to do is the difference between X and that projection of X, the distance should be minimized. So that's the meaning of the distance between X and approximated version of X. That should be minimized. Again, based on this constraint. And this is actually the meaning of the distance projected on that hyperplane. So either you can solve this objective function, this optimization problem, or this optimization problem to get the W values. But you see that SVD really helps, and it actually makes everything simpler. And I by myself prefer to have SVD version of PCA than these other methods. What intuitively this PCA does is, if you have this original data on the left hand side like this, what SVD does is actually centralizes the data, so puts the origin of the data on the central mass of the data. So here is the central mass of the data, takes the origin and puts it here, and then it actually makes a rotation in such a way that you have this y1 and y2 as the most important eigenvectors, which contain the most variance of the data alongside. So y1 has the most variance of the data alongside, and then is y2, and y1 and y2 are also orthogonal. That's the intuition of PCA, what it actually does intuitively. We have different types of PCAs. So kernel PCA, robust PCA, and they are actually the extensions of PCA. You can go to the materials and papers to get the idea of how they are derived and what they are used for. But the general thing is PCA, as I mentioned, and they are used for the compression of the data. There are some pros and cons associated with the PCA. One of the things is that PCA looks at the data in black and white, so it doesn't consider any class for the data. It just, observes the data as a bunch of data and without considering any class. So the general data, how is it scattered in that domain, and tries to find the best projections, orthogonal projections, onto linear hyperplanes that gives the maximum variance. That's all. So never considers about the class of the data. But in the case of unsupervised machine learning problems or unsupervised problems, that should be a good idea actually to use PCA. So we go to another transform which is more capable of considering the class labels for the data. If the data is not just taking out of one class, and maybe the data, you can say the data is scattering in such a way that bunch of the data is actually accumulated in some place and bunch of the data in some other place. And it would be much nicer if you see that part of the data is actually coming from some other label or other class, and the other one belongs to other class, and so on and so forth. And you actually try to find a kind of, reduction to the dimensionality of the data in such a way that these classes are also preserved. Then we are looking for something like LDA. So if you have a bunch of data like this, with class labels 1 and 2, for example, PCA just is looking for the maximum variance of the data. And it's two-dimensional. If you want to project it onto one-dimensional case, so it tries to find this line in such a way that the maximum variance of the data alongside this line will happen. And that's the best thing, because all of the data, if you just consider the variance, then that's the best line that you can have as a projection, the direction. So that's the best direction, that if you project the data onto it, then you can have the maximum variance. But it never considers about the classes 1 and 2. On the other hand, if you have a kind of projection like this, but we have not discussed about what kind of projection it should be. If you have a projection like this, then the classes are also preserved. So you are reducing the dimensionality of the data. You go from 2 to 1, but at the same time, you're somehow preserving the data classes. So these ones are projected onto this, here is shown by the histogram. But in general, they are, bunch of the data which belongs to the class 1, they are gathered all together. And those bunch of the data which belongs to class 2, they are also somehow wrapped together in that place. So you have these classes completely separable in that
like
other
we have
domain.
the 2 lines in this case.
It's just one line. It's one line. So this is the projection 1 for the PCA, and this is the projection 1 for the LDA. So you are actually moving from 2-dimensional space to 1-dimensional space. Everything should be projected onto this line. That's the histogram is taken here, actually, but we don't care about the histogram. It's just for, the clarity of the idea. But the point is that everything in this area is gathered in this area, and for this class, everything is gathered in this area. Okay? But you have this classes actually separated in a good way. So if you're looking for such kind of transform, then you're looking for LDA. These are the addresses you can refer to. But what's the idea of LDA in very simple statement? In order to do such kind of, so class separability is the core of the IDA. Class separability, and at the same time doing the dimensionality reduction. How can we come up with this projection? Well, intuitively it's very simple. What you have to do is, first of all, try to find the point mass for all these classes. So if you have, for example, 2 classes, find the point mass of first class and point mass of the second class. And it should be easily done just by doing the averaging. So for all the data X which belongs to the first class, for example, W1, you get the values and divide it by the number of the elements in that class, number of the point data in that data points in that class. So you're finding the average or the mu for that class, and you do it for all the classes. Then, in general, if you have an objective function, that objective function is actually trying to have the maximum class separability. When you when you're trying to find a projection which gives you the maximum class separability, it means that if you have a point mass, so if you look at that bunch of the data instead of the scattered version or the blurred version as just one point and the other class as one point, you will have such kind of representation if you make these 2 points as far as possible. So the distance between the mean or the point mass of this bunch of data and point mass of the other bunch of data should be as far as possible. So it means that you have this cost function, or it's not cost actually, it's a objective function, takes the point mass of the first bunch of data, the second bunch of the data, and this is the distance between these two that should be maximized. Mu1 minus mu2 is the distance between the point mass of the first bunch of data and the second class of data, first class and the second class of data. That should be maximized. But it's not enough. Why? Because that data, those bunch of data that are in the first class, the second class, and so on, they are scattered around that mean that they have. So it's better to find, somehow make a trade-off between maximizing the mean and also somehow representing the data. Because if if everything is like this, for example, if you have data like this and like this, and if you just try to find the point mass to be here and point mass to be here and project it onto this line, then all the data is actually here and here, and you will lose all the other data. You might have some information around, so it's not just these 2 points which are important. You have some information around, and you will lose over all these things. So it's better to have a compromise between maximizing the means and also, a less important thing, somehow a kind of projection which tries to have maximizing the mean at the same time having some reasonable amount of scattering around the data. Okay? So we call this between class scattering. Between class, this is class 2, class 1. So this is between class scattering. And you have also within class scattering. So this is the scattering within the class 1 and the scattering within the class 2. So in general, it gives you the idea of having a cost function, there's a say objective function, depending on the parameters which are W. This objective function represented in such a way that you have the maximum between class scattering normalized by the within class scattering. So that's the idea. And now how it's represented is here. So the objective function of the linear discriminant analysis is to find W in such a way that when you apply W to the X, the data, the original data X, what comes out of that should have this property that this is the objective function. You're actually maximizing the distance between the means, well, the energy of the distance between the means, and at the same time trying to, this S1 is the variance of the data of class 1 and variance of the data of class 2 when you do the projection. So S1 tilde square is the variance of the data projected onto that line. This is called S tilde square. And for this one, S2 tilde square. So you maximize the between class scattering over the within class scatterings. And if you do that, you're actually finding a projection which compromises between the means and the variances around. And that's the projection which gives you the best dimension, or the best actually direction which you can project the data onto which, and you can get a lower dimension of the data. So these are the derivations of the data, the transform mentioned in this slide, and there is one nice tutorial that I will assign the same as last semester. I will actually upload it for this part, You can also go through that. Most of the things I've written from that one. But in general, you see that this mean of the projection here and the mean of this projection of the second class here, which are actually represented by mu1 tilde and mu2 tilde, they are projected version of the mu1 and mu2. So the projection is W transpose. Mu1 is the real mean here, the point mass. When you want to project it onto that line, which is representing the LDA, is W transpose this mean, which actually comes to this one, mu1 tilde. And the same for the other one, mu2 tilde. And we already know that the variance can be represented by W transpose, the quantity W. So that's the projection variance. The sample variance for in a kind of so if you have the W transpose something, you want to get the variance. For example, if this is X, you want to get the variance of W transpose X. That variance is nothing but the sample variance or the covariance. So you write it down as W transpose X, X transpose W. And this is the random variable you have. Applying the E, this W comes out and becomes W transpose covariance of X, W. So anywhere that we see such a thing, it's actually, and here the covariance is mentioned by S. So that's the energy of the between class scattering. And the same way for the within class scattering, we have the S1 square and S2 square, and SW is the sum of S1 and S2. And this is the way that you can actually differentiate everything to get the values. So you get the W optimum, the best projection, as to be the result of this optimization problem. The argmax of this objective function, which this objective function is the ratio between the between class scattering, this between class variance or scattering, and within class scattering or the variance. The W that maximizes this is the W of LDA projection. And there are some, well, there is an extension for multiple classes. What we mentioned here is just for two classes, but this separability can be applied for even if you have, for example, multiple classes. Here for K classes. So in this one slide, if you want to generalize that idea for two classes to multiple classes, that's the between class scattering that you use. You just assign the probability of the data to be for any of the classes. So K classes you have. The fraction of the data which belongs to that class is actually the number of the data on that class over the entire number of the classes. And then you have the mean for those classes, and this is the mean of the whole data. This is the between class scattering, and you have the within class scattering the same way. Just you apply this weight which is the responsibility of each class to have contained that data. That's all. So the within class and between class you have, and then the same cost function, and you will get the result. So examples are in the Bishop, you can find it. There are so many examples for reduction of the data, dimensionality, using the LDAs. For the face recognition, it's something that has been already in the articles, but there are also some limitations. And one of the limitations is that it's by default is considering for every class to have the Gaussian distribution. So all the classes, for every individual class, it somehow implicitly considers a Gaussian distribution of the data over that class. So that sometimes creates a problem, and sometimes that mean is in such a way that all the means of the classes are in the same space or distance with that, then it will fail. But there's also some cases that the data is scattered like this, and maybe it's better to mention, even if it's one class, but when you apply the LDA, it assumes that it has two classes with two different means. But it's actually a bunch of data which is scattered with some irregularities here, And you see that PCA, for example, can outperform in that sense, but LDA, if you apply that, is actually considering two different classes, which is actually one class. When you have some outliers in the data, and those outliers make the different point masses, then LDA actually fails to give you the right answer for those outliers. And that was the entire thing I wanted to say about the PCA, LDA, and SVD. And there are a lot of applications that come afterwards. One application would be the compression of the data, but we should take care that PCA is actually a kind of transform that compresses the data, and at the same time you lose part of the data information. So it's called a lossy compression. Sometimes people do PCA, and then when they want to resynthesize the data to the original dimension, what they do is that they just assign, for the rest of the dimensions, they just assign different noises with different variances, add it to the data. That's what the people normally do. Okay. Any questions or anything to mention?
Sorry, can you go to page 14?
14?
Yeah.
Okay.
Maybe previous one.
Okay.
Yeah. Because in the first view we took the we take the two norms into account, and in the second view we talk about the F norms. What's the difference between these two different types?
Because there are different, we have different objectives. In the first view objective, when we say the first view and the second view, is that just the same as LDA. We had a view of having the most class separability. That was the view, and the view is something that determines your objective function. So for the first view, we have this idea to maximize the variance of the resulted projection. So if you project everything into that hyperplane, you get the maximum of the variance. After doing the projection, you get the maximum of the variance. So it means that the maximum variance of those projections. And when you have the projection, the variance of that projection data is W transpose X norm 2 square. That's the meaning of what I mentioned here as the idea. So we have to find subspace with the maximum spread of data onto it. It's just a variance that should be spread in the maximum variance of spreading the data or scattering of the data. You're looking for that. So it means that W transpose X, which is the projected data, should have the maximum variance. And to represent the maximum of this variance, you have to make it 2 norm squared as the maximum of the variance. And at the same time, you apply that constraint that W, the norm of the W, shouldn't exceed than 1. So the unity norm for that W, for that projection vector, actually. And we make it as a square because the first quantity is also squared. When the first one is squared, the second one we also make it as a square to have the same dimensionality. If it's power, it should be power. If it's voltage, you have a voltage. You cannot compare voltage and power or something, with different quantity level. So the level of the quantities are preserved, and that's a constraint. So you can, and because this objective function L2 norm squared is a convex function, because of the convexity, you can use the Lagrange multiplier and make the constraint problem as an unconstraint. It's simpler. And using the derivation with respect to W, you can get the values of W.
In this case, W is a projection vector. And
The projection vector.
Vector.
Yeah, that's the projection vector that gives you that the idea that you wanted, your desire. So based on the view, we can set up the objective function. But the PCA based on SVD is actually using the entire information in the SVD. So we say that SVD is this kind of, factorization of any matrix. So if we can leverage this idea in the SVD, we can simpler do everything, all the task of the PCA, and that's the idea. Because we know already SVD, then applying the PCA using the SVD is much simpler than going through this optimization problem. And it's much faster. If we apply the other way using the SVD, it's much faster. On the other hand, you have the notion of reduction. So you know that by playing this K, you're actually playing with the dimensions that you need. So you go for the dimensions that, for example, are unnecessary. You can get rid of those dimensions. When you are SVD, that's possible to do that. Yes?
I was wondering about the due date for the homework, whether it remains on the 4th or...
I got 2 emails so far, but if just in this session we can determine whether you need actually to be extended or not.
I think it will be better if it's slightly extended.
To be extended?
Slightly.
Slightly.
I'm on the 6th, so for me it would be very nice if it could be maybe a couple of days later, 4 or 5 days later.
4 or 5 days later. 8th of April. So I will put it in the website that 8th of April is the extension of the first set of homeworks, but I will try to provide the next homeworks probably tomorrow after the lectures are over. Then these lectures for this week I will put it again in the same way, but I will give you a reasonable deadline for that. And also I'll try to have some MATLAB examples for that. Okay.
Thank you.
You